So, all right. So DNS can have a lot of security problems, and the vulnerable situations in DNS range from configuration errors and architecture mistakes that make your DNS server itself vulnerable, so an attacker can bring it down. And then your DNS server can also be vulnerable to abuse and be used as a weapon to attack other machines. So there's lots of various ways to do it wrong. This one simple form is architecture mistakes, and until maybe 2002, it was very common for people to have things like one path into a network, one ISP, one DNS server, and that sort of thing. And obviously that's very fragile, the sort of thing that no large company should put up with, because as you know, every device will break sooner or later. So if you only have one server, it will let you down, only one switch and all that jazz. So if you have, that's one issue. And also if it's attacked, or if other things happen like fire or power failure, then it goes down. If you have a single recursive resolver inside your company, which people are using to find DNS on the outside, then if that goes down, nobody can use the internet at all in your company. So that's one of the many very rude things to happen. So in both cases, you should have an alternative. And the default setting of Windows IP settings is they always encourage you to have two DNS servers for that reason. Your client should have two choices, because if one is down, it's unacceptable to lose the whole internet. You should have another choice down there. Now, one thing a lot of people do these days is use cloud DNS servers. There are so many free ones. There's OpenDNS at 208.67.220.220. There's Google at 8.8.8.8, and there's a lot of others. Now, if you use these, experts will say your DNS service is slower, because if you had a DNS server in your LAN, it would be only less than a millisecond away. The one on the internet is probably 10 or 20 milliseconds away. But in practice, I certainly find that it's faster, because the local one tends to be down and busy and unavailable. And the cloud one, if you use those big ones, is a huge, robust cluster. It always answers quickly. One issue at your company is whether you want to monitor DNS or filter DNS. You might want to know all the DNS resolutions that your people are making at your company, so you know what websites they're going to, and you might even want to block certain websites you don't want them going to by blocking DNS. And in that case, you would want to force them to use your DNS server so you can control what they'll get to and what they won't. And if you want that, then you would have to block all those cloud DNS services at the firewall. Or, more likely, just block all outgoing requests to port 53 outside your company. You have to ask your internal server and block all those external servers. If you're happy with your people at your company using random servers all over the place, you could still monitor the traffic and pick out all traffic to port 53 and find out what they're doing, unless they use DNS privacy extensions. And this is an issue here. That one of the DNS and border gateway protocol are relics of the ancient internet, back before anybody thought about security, and they just do appalling things. And the appalling thing DNS does is it sprays every domain name you use in plain text all over the place, so it ruins your privacy utterly. So it's very nice for network administrators. You can see what everybody's doing all the time. There are some extensions to add encryption to it, but none of them are in common use. Most everybody's still using plain unencrypted DNS, which is really very strange. But there's a lot of that out there. People using old protocols that are far past any sensible time to upgrade them. So here's a DNS server architecture with a lot of points of failure. So you have the internet, you have one path in, you have one firewall, then you go to one router, then you go to a pair of servers down here. So if one of these servers goes down, you're all right. But if any of these other devices go down, you've lost the internet. And this is the way people did it around 2000, 1999, when I remember my company, when the I Love You worm came out in 1999, they called me and said there's a dangerous virus on the internet, unplug the modems. The entire company used 5 modems, and we turned them off for 3 days because we really didn't need the internet very much. Our main business happened by physical mail and fax and telephone, and we really didn't need the internet to get through the day because it wasn't that big a deal at that time. Of course, that's not true anymore. All right, so if all the DNS servers at one site go down from earthquake or something, then you've lost them all, so that even if you have a cluster, you probably want a geocluster, geographically distributed devices. And that's the way you really stay up. This is how Cloudflare stays up, and the root of DNS and Google and the really big networks like Yahoo and such. They are so big, you couldn't take Google down with an atomic bomb. All you could do is get one of their many centers and all the others would seamlessly take over. All right. So then there's configuration errors. This is a very common one, unfortunately, because of Microsoft. Microsoft Active Directory is by design practicing automatic DNS registration, so every time a machine boots up, it registers in the local DNS server with a DNS name so that Microsoft's Active Directory can use DNS addresses to find devices on the local area network. But for some unimaginable reason, it sends unnecessary reverse DNS lookups right to the root of DNS, unencrypted right out into the internet for every single device that boots up. So it announces your presence and your address to the whole world every time you boot up. It is bizarre, and it's been that way for many decades. And beyond compromising your company's privacy, it actually pollutes the internet with a large amount of traffic to where there's a special cluster of black hole servers just to try to deal with all the flood of traffic from all the Microsoft servers that keep doing this in Microsoft clients, but Microsoft never seems to do anything about it. So anyway, it's a well-known fact. Your local DNS server has a lot of data in it that you don't want the whole world to know, so you really ought to have two servers. This is the correct deployment. You ought to have a DMZ, where people come in from the internet and they go to a semi-trusted network where they don't have to pass any strict filtering to get in here. As long as they're not obviously violent traffic coming in on a goofy port or something, or a DOS attack, they can get to your web server and your email server because you want everyone to get there. Then you have authoritative DNS servers, which are used by people from the outside to find your internal servers, like these addresses here. So when they ask, where's the mail server, they'll ask these authoritative servers that are also in your DMZ. And in your internal network, your internal clients going out have a different internal server down here to serve their DNS needs, that they don't just use this one, so that when they boot up their machine and they register in Active Directory's DNS, that's all inside here. And that therefore these servers should only have the data that pertains to your public records, so it doesn't really matter if somebody gets all the data off these servers. There should be no secrets on there. There should be no secrets in this whole zone. There's an endless chain of breaches where people, like faculty at a college, will have a web server and they'll put some file on a web server, like social security numbers in it, and then not put a link to it and then imagine that nobody can see it. Well, you shouldn't be putting anything private on a web server. It's just a bad plan. And the main offender here is Google. If you put up a file and you have no link to the file, you would think, well, there's no way to click on it, no way to find it, but that is Google's entire business, is finding everything. They will find it, and they will index it, and everybody will see it. That's the problem. So you should keep it off the web server if you don't want the whole world seeing it. This is why I often get people coming up to me and saying, well, I want to put this thing on Facebook and I don't want everybody to see it. And I say, you know, this is a self-contradictory position you're taking. But I do understand that is Facebook's business model, is people like to think I could share things with just my family and all the crooks in the world won't see them. But it doesn't work very well for that, because Facebook keeps on changing the privacy settings without any warning, without explanation, and always in the direction of revealing your information, because their ad targeting relies on information being spread. And the popularity thing relies on you being connected to more people, so they will force you into that, whether you like it or not. Sort of like a nosy relative who keeps fixing you up with potential mates at a party. They keep messing with your privacy because they make money that way. So here's an example of those leaky queries. You boot up a Windows machine and it starts sending information out here to prisoner.iana.org and other strange servers. And you can, and this is a Windows 2003 server doing it, and here's Windows Server 2008 doing it from your project. If you just register your server in DNS, it will now send a bunch of these queries. What happens is your server gets a local IP address, 192.168.119 something, and then, because Microsoft is just nuts, they take a private address and they wonder if someone is already using that private address on the internet. So before letting you use it, it sends queries all the way out to the reverse DNS inaddr.arpa, which is the root of the whole DNS tree, saying, is somebody like maybe Google using this address? When it's completely impossible for anybody to use that address because it's a private address. But Microsoft did not program their server with the private address ranges, which is very strange. They're not a secret. They were in RFC 1918. They've been out there for decades. So they should know not to bother asking any public DNS server any questions about these private addresses. They will not know. But anyway, that's why they had to put up those prisoner servers, which is a cluster of servers to try to handle this traffic. And I'm pretty sure it continues to this day. One thing I haven't done yet, I got demo versions of the very latest Microsoft server, so I'm trying to put up a 2016 DNS server and see if they fixed this. I doubt it. Somehow they don't care. It's been an awful long time, and they never seem to fix it. Anyway, you can fix it. It's kind of painful. You'll do it in some of the projects. You can turn on some settings to manually block all these ranges from leaving your DNS server. And you certainly should, and that should certainly be the default in my opinion, but I'm not very often able to sway Microsoft in my opinions. All right. Another common mistake is to take your authoritative server, which is intended to let external people find your local servers, and make it recursive. A lot of people just leave it, which means that it can look up other things that are not part of your company. That's unnecessary and not a good idea. It means your server will be burdened with people looking up Yahoo and stuff and not be as available to answer the important question. It's really doing somebody else's work for them. There are a few companies that for reasons of their own, like OpenDNS and Google, choose to run public recursive servers, but those servers are not authoritative servers over anything. They, for some reason, like Google, wants to hand out DNS to the whole world. And it's, I guess, just an act of charity. Certainly, they could charge a lot of ads with that. They claim they don't, but I wonder why not. It's just a pile of money sitting on the table, and they keep saying, we're not taking that money. No, we aren't. I don't know. Anyway, but they're doing it. But you don't, these things are different functions should be on different servers. Your authoritative server should not be recursive, and your recursive server should not be authoritative or anything. You're serving different purposes. Anyway, there are a lot of open recursive resolvers on the internet. If you do make a recursive DNS resolver available to the whole world, which a lot of people used to do just through not understanding the situation very well, they just install it on a server, plug it in, and not think about it putting any access control, then it can be used for evil purposes. And so if you are going to do that, you should limit the queries. You should either limit the number of customers that are allowed to reach it, like Comcast DNS servers are only available to Comcast customers. Other people can't use them. Or if you're going to let the whole world use it, like the Google DNS servers, I think it's BCP 38, you're supposed to limit the number of queries an IP address can make per second, so they can't abuse it. There's an open resolver project out there which scans the internet and finds these and lists them, so you can see how many people have open resolvers, and nobody should have them unless they have thought it through carefully. This is like putting up an open unencrypted wireless access point. If you do that, you ought to understand that now a bunch of people are going to start doing illegal things with it, and you should have some kind of countermeasure to limit that, or you'll be sorry. And if you just casually put one up, pretty soon you'll be flooded by crime and held to some extent liable for all that. So I tested CCSF servers. At one time, I think we had an open one, but as of 2016, we no longer have any open ones. You can just dig for name servers and find the name servers, and then you can put that address range of these name servers in that other tool and see if they're detected as open resolvers. That's what I did. And that they weren't. That same guy has an open NTP server list. And NTP servers are much more dangerous. But NTP servers are so dangerous that when they're used for attacks, they typically only get used once, and then they get fixed because they bring down the entire network that's being abused. Anyway, we'll play with these a little more later. Another thing that happens is DNS zone transfers. Your servers, if they are old, this was the default, they will just let anybody do a zone transfer at any time to any address, which means that anybody can suck all the data off it. Now, if you've been deploying it correctly and there are no secrets on it, then that's not so bad. But if you have also made the mistake of letting your Microsoft machines automatically register or some other kind of data go on there you don't want the whole world to know, then that's not a good idea. And you should only allow zone transfers to IP addresses in your trusted range or something. North Korea made this mistake. North Korea set up the internet in 2016. They made one of their top-level name servers configured to allow zone transfers. North Korea made a big deal out of making their own internet and their own operating system at this time. They called it Red Star OS, and it leaked out, and it was all over the capture the flag competitions. Everybody had Red Star. You run it in the virtual machine and then hack into it. It was like Ubuntu with a whole bunch of mistakes and holes and a whole bunch of monitoring software. The point of it was the government should know everything you're doing. But anyway, this is something Iran said they were going to do. After Stuxnet, which is like the 6th or 8th massive cyber attack that the U.S. and Israel performed on Iran, they sort of said, I'm going to take my ball and go home. We're not going to use the internet at all anymore. We're going to make our own internet that will be halal and no viruses, no spam, and no rotten American or Israelis ruining all our stuff. But they haven't done it yet. But they said they were going to make their own internet to escape all the corruption of the evil world, which is pretty understandable because we've been using them for a punching bag for a long time. All right. Up the cahoots. All right, so I guess they're rotating, but there aren't any new people. Wait 5 seconds and start. Oh, they're still coming in. Okay, good. All right, here we go. If I can get this thing to work, start, I say. There we go. All right. Only 4 questions, apparently. All right, which error leads to denial of service? All right, that's a single point of failure. All right. Which error exposes your whole network diagram? All right, and that's zone transfers. All right. Which feature should not be active on an SOA? All right, that's right, recursion. All right, and what type of service is a danger to other companies? Right, the open resolvers can be used for DDoS attacks, or packet amplification DOSs. So the winners are TIP, and AE, and Blunder. I know who Blunder is. Figured that out. All right, so I think we can just carry on to the next bit here. So another thing you can do is you might run the DNS server service as administrator or root. That's a fairly common mistake. And of course, this is bad for web servers, DNS servers, and anything else, because that means if there's a flaw in the server service, like a buffer overflow, and someone's able to compromise it, they are already root. Otherwise, you have a series of escalating attacks. First, they compromise one service, then they have to escalate to local administrator, then they have to move over to like the domain controller and get domain admin, and then the delays caused by these levels of controls give you time to detect the problem with security monitoring and respond to it with instant response. Otherwise, that's why one of the fundamental errors of companies that everyone laughs at, like the domain registrars that got hacked by the Komodo hacker, are that they're a flat network with just one firewall. And once you're in, you have everything. That's quite common. And that's one thing I haven't heard them accuse Equifax of. But they don't seem to be giving any intelligent answers to any questions. So I wonder if they actually had any internal security zones either. This college really does. We have 100 VLANs. If you were to hack into something in this college, you would not find it easy at all to take over something that really matters, like where the credit cards are in the bookstore or where the grades are stored or anything like that. You'd find many barriers. It'd take you a while to dig through, and that's the way it should be. All right. Then, of course, the software has its bugs. The DNS software itself, ISC bind, is the most popular DNS server, and it's had a whole series of problems, just like Apache, just like IIS, just like everything. As people keep improving their skills at hacking, your developers have to improve their skills at building defenses, and every couple of years you find out that the previous generation of software is not good enough. So there's just an endless series of vulnerabilities. Here's ones in 2013 and 2012 and all the way back to the start. Just like everything else, there's patches all the time, and there's several patches every year that are really important, and you really have to make sure and put them on or people can take you over. Here was one in 2008 that was really nasty. You could just use a address and put some extra characters in an address and it would be executed as exploit code. These are the kind of things that come from imperfectly parsing to try to take the string that comes in and find an address. Buffer overflows is another category of it. One other category is command injection. There's a whole series of vulnerabilities where you feed it some kind of text and the engine that tries to pick the important part out of the text makes a mistake and somehow misinterprets the input. All right, and then there's source port randomization here. This is the big security improvement that fixed all the DNS servers in 2008. This is what made Dan Kaminsky famous. It turned out that the protocol DNS was designed poorly, and it had a security flaw in the intrinsic protocol itself. And that is, you have servers, and your servers, when a DNS server queries another DNS server to find a record, when it gets a response, it has to somehow tell if that is an authentic response or a response from some other server. And unfortunately, it's not encrypted or cryptographically signed. All they did was give a transaction ID, which identifies it, and the response has to have the same transaction ID. And that was the only control, because until 2008, most DNS servers used a destination port of 53 and a source port of 53 for all such queries, or at least a fixed source port, because nobody thought it mattered. So the only thing to identify an authentic response from a fake response was the transaction ID, and that is only 16 bits long. So there are only 65,000 possible transaction IDs. So if you just try to send it lies, you have one chance in 65,000 of sending it right. And that's not a terribly large number. You could imagine sending 65,000 packets before too long. But Dan Kaminsky's contribution, among others, was to find a way to do 500 guesses in one packet, or in one response. So he could guess them 500 at a time. And if you guess them 500 at a time, it really doesn't take long to try all 65,000. So he was able to poison any DNS server and make it believe any lie because it would feel like he was the authoritative person replying. And the best fix to that is DNSSEC, which actually properly cryptographically signs things with these long, random-looking keys that are essentially impossible to forge. But the short-term solution was to just randomize the source port of the query also, so you would have to guess a second 16-bit number. And that takes you from 1 chance in 2 to the 16 of getting it to 1 chance in 2 to the 32. And in practice, that made the attack so much more difficult that people didn't have to worry about it anymore. So that was like the temporary band-aid you put over that attack while you have to get you time to upgrade to a really good solution. This is a fairly common thing that happens. The same thing happened with wireless networking. Originally, wireless networking had no encryption and no concern at all. That was the old 802.2, I think, or 802.3 with wireless networking, 802 point something. And then customers refused to buy it because they said, I don't feel safe using a wireless network. It feels like my data is going all over the place. So they invented something called WEP, Wire Equivalent Privacy, which was a marketing term to convince people it was safe to use Wi-Fi, and it wasn't. Within a year or two, everybody figured out how to hack WEP because it was garbage. And so they put little band-aids over the 4 mistakes in WEP that made it vulnerable and called that WPA. While they moved to WPA2, which was actually an improvement in cryptography to a much better system, it turned out that the WPA patch was very good. Everyone thought that would only hold it for a couple of years before somebody would hack through it, but they never did. And WPA1 is quite safe even today, but WPA2 is faster and better. Anyway, that's the game here. So each DNS query and response has a transaction ID field, which is 16 bits long and supposedly random. And bind 8 and 9 actually used predictable transaction IDs. Their random number generator wasn't very random, so all you'd have to do is do 10 queries to a server and you could predict them all, so you could totally poison it. But that's a vulnerability they fixed. So here's the randomness of the transaction ID. If you just do a lot of DNS requests, you can print out the transaction ID and you see this query goes out with 668 and the response comes with 668. The next one is 8480 and here's the reply, then 78, then 93D and so on. This, I think, is a Windows DNS server, and it seems to be sufficiently random that there's no obvious way to predict it. So at least it's random, and that means an attacker would have to guess 16 bits of randomness to poison it. But here's the trick. So you want to trick a target into making requests of a server you control so you can send it lies. So what you do is you run a domain, evil.com, and you have a DNS server, ns1.evil.com. So you could send an email to the company and hope somebody will click on a link that goes to evil.com, and that will cause them to make a request to your server. You could also just send an email from an evil.com domain, because now, in order to block spam, whenever you get an email, your email server will do a DNS resolution, a reverse lookup of the from address. So you send something from Yahoo, it will check a reverse lookup to see, does the IP address this came from actually belong to Yahoo or not? If it's not really the IP address that Yahoo has recorded as the one that should be sending mail, then we're going to throw it away as spam. So that means you have no control over this. It doesn't even reach the end user. The server makes a DNS request. So I can trick your server into making a DNS request by just sending emails from me. And once I trick someone into making a DNS request, this is one of the many defects in DNS, I can then make many DNS requests. For example, I can tell you that you're looking for evil.com, but when you ask for the address for evil.com, I can tell you, oh no, it's a canonical name for www1 evil.com. So you have to ask again for that one, and I'll tell you it's www2. So if I can get you to make one request, I can get you to make many requests. It can make it take many, many, many requests to get to the end. Okay, so now I can trick you into making dozens of requests easily. You can also do name NS referral chaining, where this one has a start of authority there, this one has a start of, this name server delegates to another one, this delegates to another one. There's a lot of ways to tell it. You have to keep asking someone else, ask someone else, ask someone else, just to make you make a lot of queries to my server. And in the simplest case, I'd just be making one guess of the TXID for each one of these, and that wouldn't be too dangerous. But it turns out there's another weakness. All right. The random things here are the transaction ID and the source and destination ports, but those were not random in practice, at least not at first. And so the first response that meets those criteria is accepted as legitimate response, and that information is added to the cache on the server. So here's cache poisoning. Cache poisoning consists of sending a false record that is misunderstood by the server as an accurate record and changes their entry. So the attacker tricks the resolver. So I trick you into asking a question of my server. And when you ask that question, I tell you a lie about Yahoo. If I'm able to trick your server into believing it, your server will then put in the cache a lie about Yahoo, and now when your real clients ask where Yahoo is, they'll tell it the lie. That's DNS cache poisoning. And so I have to do things. First I have to trick you into asking me a question, and then I have to come up with an answer that will contain data that fools the server. A properly designed protocol would make this difficult, but DNS does not make it difficult enough, and this is the Kaminsky attack. So an attacker issues a query for a non-existent domain. This goes to a server, and they immediately start sending fake responses to their own query, trying to trick the server into falling for it. And as we'll see, there's ways to make it very efficient. So if you ask for an IP of an address that does not exist, .example.com, the attacker can send an answer here, saying does not exist here, here's the actual address for it, and then I can have an additional section here, and I can put more information here, and your server will believe it. Once it accepts the reply, it will accept additional information down here, which is a very strange thing, and that's one of the reasons why this attack works. You can answer questions that the server did not ask, and it will believe you. So that helps you poison it. And so here you can put image tags on a server, many of them, so it makes many requests back to my server. So if one Comcast customer views this page, then I can get the Comcast resolver to go hunt for these domains. It won't find, and it gets fake results and poison the Comcast resolver for all the other Comcast customers. That's the trick. And it can happen as fast as 10 seconds. So that's one weakness, and we'll talk more about it later. There's another one. If the attacker gets in the middle somehow, by being, for example, your ISP, or controlling your router, or just redirecting traffic with ARP, then they can see your request and the resolver's reply, and they can just alter the reply because nothing is signed and nothing is encrypted. So they have all the information they need to completely craft a lie to tell you, and you will believe it, and you end up going to the wrong site. And here's the one that we were talking about before. If you have an open DNS resolver, then all the attacker has to do is make a lot of queries with the target as the from address. And so he'll make a request and all the replies will go here. And DNS, being a UDP-based protocol, has no handshake. So I do not verify who I'm talking to before I start talking. So it will accept a packet without having any way to verify the source address. TCP won't fall for this. I have to send a SYN, then it has to send a SYN-ACK back, and I have to send an ACK before we can exchange data. So it has to make sure we're really having two-way communication between the same two machines here before we go. But UDP doesn't have that. I send a request, and all I have to do is find a small request with a big answer. And I can send a lot more traffic at the target than I was able to produce with my original attacker. And not only that, it launders my attack because this person will see the resolver is attacking them. They will have no clue who's really attacking them. All right, I've got a few cahoots about that. I'll wait another few seconds. All right. I think we got everybody we're going to get. Okay, 6 questions. All right, what weakness makes it more dangerous when your server gets hacked? All right, running in privileged mode, of course, means an attacker gets in faster. All right. What weakness makes it easier to poison your cache? All right, looks like I forgot to unmute myself. All right, now they can hear the sound. Anyway. All right, that is a fixed source port. I'm surprised Open Resolver is so popular. There's no particular reason why an Open Resolver is easier to poison. What's easier to poison is a machine that always uses the same source port. So there's only a 16-bit number to guess to poison it. All right. Which attack causes all the users of a server to see fake websites? That's cache poisoning. The server now has a lie, and everybody that uses that server will hear the lie. All right. Which attack exposes information but does no other harm? That's a zone transfer. And so I've seen people answering man-in-the-middle attack. That's interesting. Well, almost always man-in-the-middle attacks do harm, although just the fact that you're in the middle doesn't imply immediately you're doing harm. But the zone transfer just exposes the information on your server. And it isn't really an attack in any other sense. So I think I'm going to stick with the answer. In fact, I have no way to correct answers, but I have some sympathy for people who chose man-in-the-middle. But I think zone transfer is the best answer. Anyway. That's why these things are extra credit, because they're not always perfect. All right, so which attack lowers availability but does not affect confidentiality or integrity? This is a security plus question. All right, that's denial of service. That's lowering availability, but it does not involve altering data, which would be a failure of integrity, or exposing secrets, which would be a failure of confidentiality. All right, which attack lowers integrity, but does not affect confidentiality or availability? right, and that's cache poisoning. Cache poisoning causes your server to sell lies, but it doesn't go down, and it doesn't expose secrets. It's handing out altered data. That's a failure of integrity. That's what that is. The server stays up, but the results it hands out have been altered by unauthorized people. So the winners are AE, Dougie, and EC. All right. So you've got, that's it for the lecture, and you've got projects to do. Let me see which ones are due. By next time, you should be up to projects 4 and 5. So you should be down here disabling dynamic updates. Project 7 is when you do that Kaminsky attack we've been talking about. All right, and let me see how people are doing. Your scores are up here. So here's the project. See, quite a few people are up to project 3. Not too many people are beyond it. Here's a few high achievers. And looks like most people are taking their quizzes and doing well, so I think we're moving along here. Anybody got any problems, let me know. I'll go up to the lab, Science 214, for a while and see if anybody wants to work on campus and get help. Other than that, about 3 weeks before we meet again, not until October 24. Okay, that's it.